All right, I'm back for another video. So I'm enjoying this book. It's definitely, they say that I like how um challenging it's been so far, and it hasn't been impossible. I feel like statistics, data science, if this is scary, well, start looking at the advanced stuff. Like I like how it's not shying away from like real mathematics. It's actually showing you the mathematical equations. It's showing you it's not dumbing down and telling a story about the author's child at recess. It's using the mathematical terms. It's showing the mathematical results through the graphs, and it's it's not shying away from, it's not trying to be a beginner's book, and I like that. It's not trying to be an advanced book either. It's trying to at most be intermediate, and at least be enough so that you have some kind of real familiarity or skill in data science, and I love that. I feel like that's a bar that's set fairly high though, but I think it's a very achievable bar for a lot of people, especially for me. There is a broad set of algorithms. To some extent, also, the previous options would fit as well. Focused on detecting anomalies by predicting what the next value is going to be. They effectively reconstruct the expected value from history and then compare the actual value. This reconstruction process can happen using different techniques. We can use supervised techniques to build a predictive model for the next observation. Effectively, it is self supervised, where the label is the next observation. Examples of these techniques are autoencoders. It is a type of neural network architecture that intends to reconstruct in the output the signal as the input, but by compressing it. We will see this in more detail later on in the book. First, so autoencoders, what they do is uh, they reconstruct the output signal as input, and we saw that in my other series, my LPIC 1 series, converting output to input so that you can feed it back into other functions is something necessary. But in this case, the output is converted to input by compressing it first. And this is a type of neural network architecture. It's an autoencoder. The signal is compressed, encoded, and decompressed, decoded. Once the model is trained, if done correctly, the output should be very similar to the input. Why not just use the input? I hope he answers that. The assumption is that the signal behaves as it should, and the autoencoder has learned about it. However, if the input signal changes due to an anomaly, that is a behavior the autoencoder will not expect. So the reconstruction will likely not be good. Suppose we measure the error or difference between the constructed and input signals. In that case, we can estimate whether the current value is anomalous compared to the previous history, which was used to train the autoencoder neural network. I know at this point you may not understand how this works because we have not explained neural networks yet, but please bear with me for the moment. You will see practical examples of this, including autoencoders. So here's a graphic. I like hearing what ChatGPT has to say. ChatGPT isn't perfect. Nobody's perfect. But one thing I think ChatGPT is really good at is if we look at the cognitive biases. There's one bias called the availability bias, and I think ChatGPT is really good at helping you overcome the availability bias. So what the availability bias is it is a tendency. It is an inability to think, and it's obvious when you think about it. It's an inability to think about things not present in your mind. And of course, let's imagine you're in the gym and the gym doesn't have a piece of exercise equipment. The gym only has weights. The gym has no cardio. You're not going to be doing a lot of cardio. Let's say the gym has only cardio, no weights. You're not going to be lifting a lot of weights. So the things have to be present in the gym in order for you to be able to use them. And then just because they're there doesn't even mean you're using them. Let's say you're biased towards only doing cardio, you're only going to do cardio. So you can think of your mind that way, like a gym. And then, so let's see what this has to say. So what ChatGPT can help you do is put more things in your gym. Now you see what the things are, instead of just you can see the broader scope, the broader picture. Before you would have to let me ask ChatGPT. Let me talk. Okay, here we go. So one of the things I really like about this program, about ChatGPT, is I think it can really help people overcome the availability bias. So if you think of your brain, or if you think of a human brain like a gym, the availability bias, in my opinion, is like if you have a gym that doesn't have any weightlifting equipment. Now, and all the gym has is cardio equipment. So the person in the gym exercising will only do cardio because the weightlifting equipment isn't even available, and vice versa. So you can think of your brain that way. If all you have in your brain are certain things, then you're incapable of using the things not in your brain. So I think this is where ChatGPT fits into the picture. It can load your brain up with a wide view of all of human knowledge, so there's nothing that you just never have heard of before, unless it's never been heard of by ChatGPT. But if that's the case, then it's just not in the purview of human knowledge at all, which is fine. The problematic things can happen when you're trying to work on something and you just didn't even know a critical concept that you needed to succeed at your work existed. Right. Can you create a so like what would you call a tool that is like not like a tool like AI or Chat GPT, but like what would be the name of a tool you could use to fill in this gap? So like for example, a umbrella like covers stuff, or like a blanket covers a bed. So like what could you build that would address the availability bias? Yeah. Okay, so here's what I'm thinking. So you know about the tree of life for biology, right? Like we share common ancestors all the way back to where there was like nothing on Earth. It was just like a rocky, uninhabitable place like Mars or the moon or whatever. And then like something happened, like a asteroid strike, or like the weather conditions became right so that like friggin' like Higgs boson particles popped into existence in the exact right way, or like something happened just right so that there became matter capable of the process of evolution. So then the process of evolution happened in the tree of life. The tree of life shows this process of evolution. It shows how that happened. So like starting from the first original and true, so the first thought, and I would say that the first actual real documented thought would be, I think therefore I am. So if we start, and let's be clear here, we're not talking about philosophy, we're talking about the human mind. And instead of the tree of life, we're talking about the tree of knowledge, and we're talking about kind of an evolution of a person's thinking and how to get that person to think in the most effective way possible. So I would say the first thought capable of the process of evolution of thinking to get somebody to the point where they can easily pass a PhD, they can easily perform valuable work, they can easily do the things required to have a successful relationship or community, or to improve the things around them, or to have the discipline to accomplish long-term objectives, to make good financial decisions. I would say that these are all things that evolve from thinking, and people who don't have, people who have mental disabilities can't do the same sorts of things that people who don't. And I think the first thought is, I think therefore I am. Like I think that should be on the tree of life, the first thought, and then off from there should branch other thoughts that evolve from that. So can you help me create that? Please create for me a tree of thinking that is similar to how the tree of life is to biological evolution. Create something like that for me, but instead of for biological evolution, create it for evolution of thinking. Is that a good foundational thought, though? Is that a good foundational thought, though, or would there be a better one? Yeah, it's famous, but that doesn't mean it's. But it's okay. Yeah. What if we do this, and just for the trunk of the tree we have I, and then like the first branch of the tree is I then you, I and then you. So like the tree forks off right at the beginning with thoughts about yourself versus thoughts about others. Does that make sense? Tell me all of the fundamental aspects of cognitive development in a way that helps me overcome the availability bias. And I'm way off into the weeds. I apologize for this. Sometimes. Oh, here we go. Man, there's a lot. All right. All right, I found the right term. Politics. I think it's. I don't think it works. I don't know. I just don't think this works. So tell me what's the difference between a oh shoot, it's a uh phylogenetic tree. So like tell me the difference between like a phylogenetic tree for biology and this. It's like, like there's a big missing piece of the puzzle in trying to just build a biological phylogenetic tree for things other than biology, because like the connections, uh like the most recent common ancestors are based on like real observations. They're not based on whatever I am doing here, or whatever we're doing here to try to do a similar thing for, like, the human brain, or like thinking. It's like, so tell me what that difference is. Like what are people noticing in biology that allows them to draw that tree in that way and have that be scientifically valid and accurate, and what is missing from what we're doing here where we can't do it with the same level of validity? What would we have to do to make our tree to make our tree for our subject as valid and scientifically legitimate as a phylogenetic tree for biology? Yeah. Right. We need empirical data. Well, dang. How can we get. Yeah. Right. And they're different from. Right. All right. And I don't want to be on a tangent all day, so I got one more, and I'm cutting myself off. Okay, so one final question. Assign a letter grade to this conversation. Now, instead, I'm reading a book on machine learning for network and cloud engineers, and this is kind of a tangent. It's a rabbit hole based on my own curiosity. So I am a network engineer. The book is very relevant to me. The book will likely lead to more career opportunities. So assign a letter grade to the time I spent having this conversation, which was just kind of in an undisciplined way, following my own curiosity and just kind of having a conversation for the fun of it, versus if I were a more disciplined person and I kept reading the book. Yeah. Yeah, I just need to. Okay. All right. I feel good about moving on. So, yeah, sometimes my security, my curiosity gets the better of me, so I kind of go into rabbit holes. I'm gonna ask it about this drawing quick. All right, we're back. So, okay, so there's the graphic. You may find many other examples of techniques with a similar underlying principle. Find a mechanism that can be used to reconstruct the that signal, given how it is supposed to behave. Um, and I just need a break. I'll be right back. All right, I'm back. Already a half an hour and didn't get too far, so I'm gonna try to stick to the content. One such mechanism is principal component analysis, another approach to reconstructing the signal. So this is a mechanism uh, that can be used to reconstruct the signal given how it is supposed to behave. Alternatively, you can use correlation indexes, Pearson correlation, for example, that provide a way to characterize the behavior of a data sample. If correlation indexes change, it is an indicator of an anomaly. We will see PCA, which stands for Principal Component Analysis, in the next channel and evaluate correlation techniques in practical examples. Key takeaway: what is an anomaly and what is not always subjective and interpretable? Oh, I see. So, what is an anomaly and what is not is always subjective and interpretable. So that's why we use these techniques we learned about to more definitively prove through mathematics that something is in fact an anomaly. It requires context and human domain expertise to properly assess the true nature of the observation as anomalous. And these human domain expertise and context can be aided with these mathematical principles that we learned about. Dimensionality reduction. You may have heard the saying, garbage in, garbage out. I will repeat it throughout the book, but it is particularly relevant in this section. We may have many data points collected in a network or cloud infrastructure. Very frequently, we may have an excess of data. People often generate the misleading perception that in the context of machine learning, you push all your data to the black box and the magic will happen. This cannot be further from reality. Any data that is not relevant to the problem you are trying to solve will result in trouble. At the minimum, it will make your systems consume more resources that would not be necessary otherwise. But it may also end up creating issues in producing the outcome you expect. Suppose you want to build a mechanism to predict a network quality KPI, which stands for Key Performance Indicator, based on the number of customer tickets opened. You may be wondering if there is some relationship between specific network metrics, such as the number of configuration changes, memory utilization, number of users, interface flaps, maintenance windows, etc., and customer tickets. You come up with 20-ish different metrics that could be impacting such network quality KPI, key performance indicators, that you do not know precisely how, but it is a reasonable guess. In this context, your goal is to build a model that allows you to predict such a KPI as accurately as possible, given those input metrics. If you do that, you may be able to figure out what the impact could be if you change any such metric, and therefore plan strategies to improve your network performance. Now the question is, are those 20 metrics genuinely relevant? Or more precisely, are they equally relevant? Or even relevant at all for the problem we're trying to solve? Ultimately, for a challenge like this, the question lies in what degree of information each variable is contributing to the problem. If a variable is not carrying any type of information, then the best thing is to remove it from the equation. As referred to earlier, any variable used that does not carry valuable information will consume resources, complicate and enlarge the size of the models to be trained, and end up likely interfering with the quality of the outcomes. The goal of the techniques under the umbrella of dimensionality reduction, so we have the word dimension and then ality, dimensionality reduction, is to eliminate those unnecessary variables or transform the input variables into a more reduced set that carries the same or almost the same amount of information as the whole initial set, but more efficiently and compactly. You could think of this as a compression technique that eliminates redundancy. So we've got we've got 20 input variables coming into the dimensionality reduction. Now we have 12 variables that we can feed to our predictive model. and from that get a network quality KPI. Let's see what the AI has to say about it. I like typically what the AI has to say is pretty useful.
Of network quality KPIs. The dimensionality reduction step is likely aimed at removing redundant or irrelevant information, which can help improve the efficiency and performance of the predictive model.
All right, and looks like there were unfortunately some audio issues in this video. I was not capturing the output properly, so a lot of that big tangent I had was not available to hear. So I apologize for that, but maybe that's a good thing because it was unrelated to the book. So that's kind of a indicator that that section was should be edited out anyway. So okay, so this is a and let me do this again now that I'm not distracted by let me just regenerate. All right, you know what? I'm fine with that. I'll refresh this. Okay, so one of the most common techniques used for dimensionality reduction is principal component analysis, PCA. The critical ingredient to perform PCA is information. In mathematical terms, the amount of information contained in a particular variable is represented by the variance. The higher the variance, the more information. On the other hand, the degree of linear relationship between two variables is referred to as the covariance, aka Pearson's correlation. If the covariance is 0, these two variables are truly independent or orthogonal. If the covariance is 1, it means they are linearly aligned. They both carry the same level of information. We could obtain the other one with a linear transformation by having only one. Hence, one could be removed from our data set. Given this, PCA, which we remember stands for principal component analysis, will produce a new set of variables orthogonal to each other in an n-dimensional space. That means their covariance is 0 and ordered in terms of variance from top to bottom. This set of variables can be maintained using a linear transformation matrix multiplications using the so-called eigenvectors from the original set. Now this new set of variables still has the same number of variables as the original one. So what have we obtained then? So we can see in our graph here, we've got numbers of VLANs used, a number of ports used. So we've got some data here. Typically, the more VLANs and the more ports. Typically, there is looks like a strong linear correspondence to the number of ports and the number of VLANs. As the number of ports increases, the number of VLANs used also increases. So we've got our ports here, number of ports, and our number of VLANs fed into the PCA, which we remember stands for principal component analysis. And then we get we're tossing out 4% of the information, The significant change is that the new variables are orthogonal, and we have a quantified view of the variance from each eigenvalue. That means, and let's get the pronunciation of this. We live in the real world, so the real virtual world. So
Eigenvalue. Eigenvalue.
Yeah. All right. So the significant change is that the new variables are orthogonal, and we have a quantified view of the variance from each eigenvalue. That means we can now choose what variables we keep and which ones we discard, and fine-tune what percentage of the original information we retain. Looking at the example in the above diagram, we can perhaps reduce the number of variables to half and still keep 96% of the information. Losing such 4% of information brings additional efficiency and gains from fewer variables. So I'll bookmark this, and I want to hear what ChatGPT has to say about this.
The image you provided depicts a graphical representation of principal component analysis, PCA, which is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. On the left side of the image, there's a scatter plot of data points with two dimensions, the number of ports used on the horizontal x-axis, and the number of visits made on the vertical y-axis. There are two vectors, A and B, which likely represent the first two principal components found by the PCA. These components are the directions in which the data varies most. Here, A is the first principal component with the greater variance, and B is the second one with less variance compared to A. The middle part shows the process of PCA with the vectors P and B feeding into it. This suggests that PCA is applied to the data to find the principal components. On the right side, it explains the outcome of the PCA. The process has reduced the dimensionality of the data by keeping the component A that contains the majority of the information, 96%, and the starting component B that contains only a small part of the information, 4%. This kind of dimensionality reduction is useful to simplify the data without losing significant information, which can be helpful for visualization, noise reduction, or to improve efficiency in machine learning algorithms.
All right, 9, 10. I'm doing my wrist exercises too. That's good. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So there are other algorithms for dimensionality reduction, such as factor analysis, truncated singular value decomposition. So those are the two we're going to focus on. These two, as well as PCA, are all linear. So let's go back. So FA stands for factor analysis. SVD stands for singular value decomposition. And PCA stands for principal component analysis. And these are all linear algorithms for dimensionality reduction. There are scenarios, however, where the relationships among the variables are more complex and non-linear, which requires non-linear transformations. I will not describe those algorithms. That's more advanced. This book operates at the beginning to intermediate level. Simply mention them, like the T-distributed stochastic neighbor embedding, TSNE. We will see the applicability of TSNE in one of the practical use cases to visualize complex data sets in a two-dimensional space. For now, I want to ensure the goals of dimensionality reduction are understood, and the key algorithms are understood as well. All right, so I feel like I've overcame a bit of availability bias. I know that they exist now. Do I understand them? Perhaps not so much. I don't know what my goal is for this series. I think my goal is primarily for now eliminating availability bias and just being familiar with this stuff. So let's move on. Key takeaway. Any input variable that is not adding enough value is consuming resources unnecessarily. We need to optimize the number of variables for any use case. Otherwise, we will face garbage in, garbage out. All right, so let me check the time. I might need a little bit of a break. I feel like this is a logical pause point. We're at the 45-minute mark. You know what? I think I might do another video this morning as well, but I'm gonna take this logical pause point, and if I do more, I'll do it in another video. So thanks for watching. See you in the next one.